Hello everyone, my name is Xingyu Wang from Northwestern University. I think it's obvious, but I will just make it clear again that I'm here. So the presentation is all about what I found. Here I'm sharing the insights and results come from the discussion with many people, including Jorge, Vikram, and Umut and Kirsten, and many others, I believe. So during the presentation, if you found that if you have some more comments on the results or you think there are ways to refine it, please definitely let me know. And for instance, I think in this slide, I think one of the most insightful and the more useful results is from Kirsten. And Umut has already given us a briefing about the problem. I believe for those who have seen it for the first time, I believe you already found it very interesting, just like we did last week. So that's the motivation of the discussion. And there's again, a setup of a problem, and some of the notation is slightly different, so I'm apologizing for this. And I think I'm adding some assumption here just to make the presentation simpler. But okay, here's the setup. So these xi are the random variables, non-negative, and they have regularly varying laws. The power law index is less than 2, so we are considering a case where they have this variance. This is order statistics. Again, considering a slightly simplified case where none of them, almost surely there will not points, there will be no times, but this can be safely generalized. And the compression problem is, let's fix the ratio z. Here we're only going to keep the top z proportion elements. So if the original vector is noted as bold x, where we keep all the elements, then after only keeping the top z, which means here's a truncation threshold based on the empirical 1 minus z proportion quantile, 1 minus z quantile, we're only going to keep the ones that are larger than this empirical quantile. So this is what we have in the end. And my impression is, we already know that under even more general settings, we already know that. So the numerator is the squared L2 norm, so it's the smaller elements. So the ones after removing the top 1 minus z proportion, after removing the top z proportion, denominator is just the original vector. I believe it has been known already that this term goes to almost surely goes to 0. What we're interested in here is, do we have a control or some characterization on the decaying rate, say in an almost sure sense or in a always high probability? In particular, can we have this control in a more explicit way so that we know, say, how it depends on d, what exactly are the leading coefficients, so we can actually apply them in practice. And here's just the intuition about how we're going to approach this problem. We're just keeping some of the main objects here. Again, xi are the ID copies of this random variable x that has regularly varying laws. Because we're considering these L2 laws, so it's more simpler to have a y defined, which is just squared x. Y will be regularly varying with tail beta. Beta is just alpha over 2, which is between 0 and 1, and y over beta is larger than 1. So the first thinking here, which is probably obvious, that is, this truncation using empirical quantile, it should be almost the same as using the true quantile when d is large. So the first thinking here is, here kappa is the exact one, is a true quantile for 1 minus d proportion. Then, again, here we are, y are the squared x. So when we're considering this term, which is truncating things using empirical quantile, it should be almost the same as the truncation under the true quantile. After we do this, for the denominator, again, this is just intuition, so this is more or less an informal statement. But under a scaling of order roughly d to the power of 1 over beta, which here beta is regularly varying index for y, this should converge to a beta stable random variable. In other words, for the denominator, we roughly know the order of this term. For numerator, I'm actually just using a very brutal bound. That is, every random variable here is bounded. So I'm using the largest possible value bounded. If you use a Cramer's theorem type argument, you're going to have a tighter control over, it's not going to be kappa squared. You're going to have a tighter control. But that's just telling us the order of the numerator and denominator. because 1 over beta is larger than 1, so we have some room to squeeze here. That is, which if you choose a 1 over d to the theta term, where theta is between 0 and 1 over beta minus 1, this eventually will be smaller than this term. So that's just the intuition. What we're going to do is just to make them precise. So the first step, I think is very standard. I'll make it real quick. So go from the empirical quantile to the true quantile. Kappa is a true quantile. I think there are many ways to do this. I'm just showing one of the standard ways. That is, we nudge it a little bit, give it some epsilon buffer. In other words, we consider the z minus epsilon proportion instead. So yeah, I just nudge the probability a little bit. So the proportion instead of z is z minus epsilon for some small epsilon. This is a term we're considering. In the case that the empirical quantile is less than the true but not quantile, we have this bound already. So it's almost the same as truncated by kappa, but just a slightly larger number. Then we'll have this bound. The chance of this not happening, in other words, the chance of we having a bad case for this to happen, meaning that so each x will be an ID random variable. The chance of them crossing kappa epsilon will be z minus epsilon. So for this to happen, that means there are d draws of these Bernoulli trials. For some reason, even though their mean is z minus epsilon, their running average larger than z. So this goes back to a Kramer's theorem type of regime again. And in fact, just use Chernoff bound. You will make the coefficient explicit. And also, you can apply Baruch-Cantelli to know that this almost surely is going to happen. It's going to stop happening after some d. So this is a tighter bound even for almost sure type of control. And you have explicit coefficient here. Moving on to the next step, that is to get the bounds. I think I will skip this part because the gist is just that we can't get almost sure bound, but the coefficient will, I guess, inevitably depend on the fluctuation of the path over that path. So even though the order should be correct, it holds in the almost sure sense. Maybe this is not the most useful bounding practice. And here comes the high probability bound credited to Kirsten. I think it's she proved it in a really simple but elegant way, and the results very insightful. So here, just to make the presentation more simple, kappa square is noted as some constant c, and I'm keeping all these elements here. She fixed the order of a term that PD is 1 over d to the power of 1 over beta minus 1 minus beta. Theta is a small parameter to make sure that this is still larger than 0. So this index is larger than 0. All right, so we're analyzing the probability of the rare case that the numerator is larger than the denominator. So the sum of the small elements for some reason is larger than the certain proportion, a PD proportion of the entire norm. This is an event we're trying to bound. Again, a very crude bound. That is, just use C to bound all the terms here. Then the upper bound is B times C. The lower bound for this term is PD times the maximum value. Instead of getting the sum, I'm just getting the maximum value over yi. So as long as one of them is larger than, say, DC over PD, this is not going to happen. Then it's, yeah, here's just some algebra. Oh, let's on the next one. Okay. So this is that for D of these elements, none of them is larger than this quantity. So very quickly you get this explicit form. This far back is just a tail PDF. Here's some manipulation, but the gist is that y is very varying. Once you have this form, it's very easy to evaluate all the following terms. What she got in the end is that here is an exponent. The probability is decaying exponentially fast with respect to d. So this is an insightful and very useful bound. And actually, that's pretty much it. So first, as I said, we add some assumption here just to make sure the presentation is more clean. We can definitely drop some of the assumptions. For instance, what Kirsten did here, I believe the regularly varying condition is not necessary at all. So you should be able to safely drop it. And another line of thinking which we didn't get a chance to explore is that it's brought up by Vikram and also Kirsten. That is, if instead we consider a stronger assumption, that is the so-called second order regular variation conditions, then maybe we can also get a tighter control on the rates involved in the convergence. But that's something we haven't explored yet. So please let me know if you have any comments, or say during the past few weeks, it so happens that you say you found an even tighter control over this. So yeah, that's all for the updates.